Welcome to the deep dive. We're super thrilled you are joining us today to unpack all of this.
Survey considerations for the physical orientation of the vehicle itself.
Let's get into it. If the mission involves high flight and low flight, a separate patch test report must be prepared for each individual AUV for both flight regimes.
Right.
What exactly is the mechanic of a patch test?
A patch test is a rigorous physical calibration of the sonar equipment. When engineers bolt a multi-million-dollar multi-beam sonar head onto an AUV, they use precision tools, but there will always be a microscopic misalignment.
Like, the sonar might be pitched up by 1/10 of a degree, or rolled slightly to starboard,
Exactly.
and 1/10 of a degree sounds meaningless until you realize that air is projected through hundreds of meters of water. A millimeter of misalignment at the sensor geometrically expands into meters of error by the time the sound hits the seabed.
Precisely. If the AUV thinks it is looking straight down, but it is actually looking slightly left, it maps a phantom hill where the seabed is flat.
Wow. Okay, so how do they fix it?
To fix this, they run a patch test. They fly the AUV over a distinct known feature on the seafloor, like a shipwreck or a sharp rock outcrop.
Okay.
They fly over it in opposite directions and at different speeds. By analyzing the distortions in the resulting map, algorithms can calculate the exact fractional degree of pitch, roll, and yaw misalignment.
They then apply that angular correction factor to all subsequent survey data
Correct.
for high flight and low flight. If the sensor is bolted onto the metal chassis, its physical alignment doesn't change based on altitude. Why do they need a different calibration for flying high above the seabed versus flying close to it?
Because the medium the sound travels through changes. The ocean is not just a uniform bathtub of water.
It's heavily stratified, right?
Yes, it is heavily stratified by temperature, salinity, and pressure. These layers are called thermoclines and haloclines.
And the speed of sound changes drastically as it passes through different layers.
Right. When a sound wave hits a thermocline at an angle, it bends, it refracts, much like a straw looks bent in a glass of water.
Ah, rebending.
Yes, ray bending. If the AUV is in low flight, just 20 meters above the mud, the sound wave only travels through a uniform layer of cold bottom water, no refraction.
But if the AUV climbs to a high flight altitude of 100 meters,
Its acoustic pulses might have to punch through two different thermoclines, bending the sound wave significantly before it hits the bottom.
so a physical calibration offset derived in low flight becomes mathematically invalid in high flight because the refraction physics have completely altered the acoustic geometry.
Exactly. Absolute rigor. You must prove your sensors are calibrated for the specific water column dynamics of every flight path.